have lecture summary for week 2. For week 2, we learned about temperature scalar quantity and heat transfer or heat transfer rate or heat flux. They're going to be vectors, so they have a direction. It can be a positive direction or negative direction. That is why it is important for us to see what is the direction of x or y axis. Then it will be useful to have the vector and the direction. Because it is the heat transfer rate or heat flux, they are vectors, we need to see what coordinate system is important. So it can be a rectangular, cylindrical, and spherical coordinate system. And to simplify any type of problem, we can consider a steady state problem, which we don't have the effect of time, or transient problem, or lump system, which means we have a time variable, but we don't have the position effect. So remember the example of potato inside oven. I can consider potato has one temperature, 100, 150 degree, but I'm not going to consider different temperature inside my potato. Whole potato is going to have one temperature. Or we can simplify any type of heat transfer problem to one-dimensional, two-dimensional, or three-dimensional cases. For example, here you can see we can consider, for example, the investigation of the window as one-dimensional because the effect of heat transfer in the x and y direction, they are a little bit much more smaller than the primary direction, so we can consider one-dimensional. Or if we have a very long rectangular bar, we can consider 2D case because at the direction of the bar, we may have a very small variation of heat transfer. And then we talked about the importance of the slope because everything in heat transfer is about the variation of temperature and how fast we have this variation happening. That is why the slope, which is the mathematical representation of the temperature gradient, is going to be very important. And we considered temperature heat transfer rate to be in any direction. And we investigated one first case when we have heat transfer in terms of conduction phenomena inside a wall. And we extracted this formula which the first term we called it diffusion term, heat generation term, and transient term. And if we had any problem without heat generation, we can get rid of it. If it's steady state, we can get rid of it. And we talked about if the K, which is thermal conductivity, was a constant number, we can take K out of differentiation, or if it's variable, we need to keep it inside. So you can see steady state with heat generation equation, transient with no heat generation, steady state with no heat generation. So there are different variation of the diffusion equation we extracted. If it's in cylindrical coordinate system, the formula is going to be this one. And you can always convert rectangular coordinate system to cylindrical coordinate system or spherical coordinate system. We just need to know what type of the equation they are. And again, same thing, we can consider with or without heat generation and transient term. And this is the formula for the spherical coordinate system. And we also introduced this formula, which is the general representation of the one-dimensional heat conduction. If n is 1, it can be we can consider this formula as a heat conduction in a wall. If it's 0, it's in conduction in a wall. If it's 1, we can consider a cylinder coordinate system, and 2 for sphere coordinate system. When you consider 0, instead of r, you are going to use x. That's it. If it's three-dimensional, you need to include the other dimensions, which is x, y, and z, and solve this equation. Of course, three-dimensional equation would be a little bit harder, and we have a name. If we have steady state with heat generation, we call it Poisson equation. Without heat generation, with transient time diffusion equation, and steady state no heat generation, we call it Laplace equation. So these are the very famous equations and available for us. These are the coordinate transfer. Later we can check them. And I showed you 6 different boundary conditions, which was a constant temperature boundary condition. Basically, you assign specific temperature to the left and right side of your geometry. And the second one, we could have heat flux assigned to the as a boundary condition to your differential equation, which is a conduction equation. As you can see, this is a specific heat flux assigned to the left or right. And if the heat flux is 0, it means we have insulating layer. Then we consider a specific case when we have same condition left and right side of our wall, and that is why at the center line or plane, we are going to have 0 slope for temperature, so dt over dx is going to be equal to 0, and that is why we have no heat transfer at that point, and we can consider half of the geometry and do the simulation for half of it, because at that line, heat transfer rate is 0. Convective boundary layer, we can have a convection on the left side or right side, or radiation boundary conditions, which is we can have a radiation left side or right side. And the final, another one was interface boundary condition. Basically, two surfaces have a plane interface, and so the temperature here is going to be same, and the gradient of the temperature from the left side and right side must be same, so we shouldn't have broken line there if it's in a perfect condition. And that is why you can see the boundary condition for when we have interface. Okay, and I showed you one method how we can extract a formula. Basically, this is when we have steady state with no heat generation with 2 boundary condition, which is a specific temperature assigned for us, so we can integrate this equation twice, find constant numbers C1 and C2, and when we find those constant numbers, we can extract the final formula, which is the temperature profile inside our wall. And you remember, temperature profile or temperature formula is the most important parameter we are looking for. We can extract any other parameters from this one. If it's cylindrical, this is the cylindrical formula. When you have a conduction inside cylinder, again, same temperature, boundary condition, constant boundary condition, we apply unit again in integrate twice. When we integrate twice, we are going to reach this formula. You can see it is going to be ln formula. So inside cylinder, we know the profile is not going to be linear as the previous one when it was conduction inside the wall. You can see it's a line, but here it is linear, so it's going to be a bended surface. And finally, for the spherical coordinate system with the similar boundary condition, we reach this formula, which is 1 over, so the formula is like a y equal 1 over x, because we have r here. So again, if we have a spherical geometry, the temperature gradient inside that sphere is going to be again bended surface. It's not going to be a straight line. Then I didn't explain this part, but you can read later. We can extract more formulas out of the formulas we have to get the surface temperature or the maximum temperature between left and right side of those geometries. Later, have a look at these formulas. It's not, I don't need to explain further, but if you're interested, just check these formulas. And then what happens if we had variable thermal conductivity? This slide shows the case when we have variable thermal conductivity, and we can take our formula K out of the integration. And you can see here for 3 cases of plane wall, cylinder, and sphere, and usually we need to have the formula of K in terms of temperature out of this graph or any graph you're finding in literature or your textbook to be able to integrate it and finish our calculation. Let me check. This is our summary page. At the end, I just want to tell you, not giving enough boundary conditions can result with a problem with our differential equation, and we can't solve it. And not giving suitable boundary conditions also can have this problem. That is why I included this part at your summary page. You can see for the first part, we have a constant temperature and heat flux assigned to the wall. So we can, for the case of diffusion equation without heat generation and at a steady state, we can solve this equation and get a unique solution. If you had two same heat flux at a different direction applied to the left side and right side, this you assign 2 boundary conditions, but these boundary conditions, they're not enough to solve this differential equation, and we are going to have no solution. If you assign q dot to the left and right side at the same direction, again, you assign 2 boundary conditions, and you're expecting to have results for your differential equation, but this is going to result in multiple solutions. So the B1, no solution. The C1, you have multiple solutions, so no unique solution. So you need to consider boundary conditions, which is going to result in a solution, a unique solution. Otherwise, the calculation won't be useful, or the boundary conditions selected won't be useful. Okay, see you next.